Hello everyone, welcome back to the stream. My name is Garrett Schnack and I am one of the co-captains of Robotics. I hope you are safe and in good health during this pandemic. Today is the second day of our Industry Professionals panel, and I hope you're excited to see the wonderful people we have here today. But first, to give you some background, we are an FRC team based in Long Beach, California at Polytechnic High School. With the 2021 season being our fourth year as a group, our team consists of around 35 student members and 5 experienced mentors from the greater Los Angeles area. During our years as a team, we have sent a robot to the Del Mar Regional, LA and OC Regionals, and the World Championships in Houston. The team has also been recognized with the Rookie Inspiration Award and Judges Award, and as an outstanding STEM program by the Orange County Engineering Council. We have a mission to enable students of all backgrounds to enthusiastically explore the various fields of STEM, while equipping them with the skills needed to succeed later in life. We take pride in providing a diverse, inclusive, and equitable environment for members to thrive. Now let's get back on track because today we are here to listen to how professionals in the industry use STEM in the environment. Not me. Let's pass the mic over to our host, Khansa.
Thank you, Garrett. Hello and welcome to Rabbotics FRC Team 7042's Industry Professional Panel with the theme STEM in the Environment. My name is Khansa and I will be your host and moderator for today's event. But before we get started, I want to go over the schedule of our event. So this event was held over this weekend, but if you missed the first day, don't worry, you can always watch the stream on our YouTube video. Today, we will be hosting 2 panelists. Each will first give a short presentation about themselves before we open the YouTube chat to our audience to ask questions. I will be monitoring the chat during the Q&A session, so ask any and all questions you would like. Please note that we have allotted some extra time in this stream to accommodate for any of your extra questions and also any technical difficulties that may arrive. So without much further ado, let's introduce our first panelist. Our first panelist is Mr. Khansa, Engineering Director at DMC Power. Mr. Khansa is a mechanical engineer who works in design, development, and manufacturing, including stress analysis on hydraulic tools and electrical analysis on electrical connectors. So please give a warm virtual hand to Mr. Khansa. Mr. Khansa, if you could please turn on your camera and you can start screen sharing the slides you have prepared.
Hey, good afternoon, guys. Thank you for inviting me. Let me start sharing my screen. So first, I would like to introduce myself. My name is Khansa. So a little bit background about my education. I have a bachelor in mechanical engineering, and I got a master's in design and manufacturing. And my thesis was about composite material and neural networks. And I got my master's from Cal State Long Beach. And it's good here to mention that whenever you want to study something, you have to look which university has a program that you would like to study. At that time, I wanted to study CAD/CAM, computer-aided design and computer-aided manufacturing. And California State University in Long Beach had very wonderful programs. So that's why I went there to get my education. After that, now I'm working as mechanical engineer, and my title is Director of Engineering. And that includes engineering and research and development. And as we go through, I would like to really walk you through what we do, what we study, what kind of environment you will be working on or doing as an engineer. Before we go there, I would like to mention that why I became an engineer and who should become an engineer or study engineering and who should not, Engineering is like, being a musician. If you don't have the talent, you don't have the passion, you'll not be successful. Even though if you study it, you'll not enjoy it, So whoever enjoy math, you enjoy physics, but you want to apply that in real life. you want to invent, you do research, you do testing, you develop things, you find solution to ideas. Then engineering in general is a field that you should join to, if you don't have passion for math or physics or that, you will not be successful. So whoever really like to apply the theoretical thing in math and physics into actual things, turn new ideas based on the laws and theories that he has, then engineering is a field that you would like. As where I work in a company called DMC Power. What we do there in DMC Power is a company that we make connectors for substation and for transmission lines. As you know, when you generate electricity, you want to transfer the electricity from where you generate it to where it's going to be consumed. And you use for that, transmission lines that you see like big, high pole or towers, with a lot of cables running miles, hundreds of miles. Those cables should be connected to the tower. So we use this type of fitting to connect them. Now, when you want to use that power, you bring it down to what's called substation. So substation, they bring the electricity from transmission lines where the voltage is very, very high and 500 kilovolts sometimes. And they bring it back to the volts that we can use in our houses. So inside substation, you have cables that you have to connect, to conduct electricity. And you have solid members to conduct electricity. Instead of cable, it's like solid tubes or solid flat bars. And you can also make connectors where you can ground the facility. So if you have fault current, instead of, if you don't want anyone to get hurt, machines not to get damaged equipment, then you ground it, using grounding connectors. Now, how we do that? We put the cable inside the barrel and we squeeze the barrel. We use for that electrical pump. That electrical pump has oil in it, and it really push the oil to 10,000 psi pressure, and that pressure will convert into axial load in the tool to become like axial force to really squeeze the tube on the cable or on the conductor. So that forces can vary, in our tools between 45 tons to 125 tons. And here I'm gonna show you a short video about that, commenting on it as we go. Again, always safety. These are some crews trying to install some connectors. Again, the idea, you want to establish electrical and mechanical connection between the connector and the conductor. As you can see here, you have a cable and you have our connector. You have solid tube and you have our connector. And to do that, you have here is a pump and here is a tool. And again, you connect it, so you use the pressure from the hydraulic oil to transfer it to axial forces in the tool. These are the things that you need to really, you need to have extra oil, Sharpie, gauge to really gauge your swage after that. And here is the connector. It has some information about it, work order, part number, inspection gauge to use, the tool to use, where to swage or where to crimp. It says swage between these two lines. And here is now an example of how you can use our connectors. Assume you have long cable. This is just for demo. So you have to put the cable inside the barrel. You measure how much you have to insert it in. You brush it to remove the oxidation layer because it will work as insulator. So you don't want that. You put it inside. And this is a tool. And this is a die that will collapse radially to really form like a swage ring on this connector. And it says here swage here. So after you put the connector inside the thing, you see you are now squeezing it. So it gets squeezed and the cable will be locked inside the fitting. So you establish electrical contact and mechanical contact. After you do that, you have the inspection gauge that you can use to make sure your connection is good. Here are some examples. Solid buses, and here are the connectors, cable. There are a lot of configurations. Some of them are splits, is for use, different sizes of the tools. So a lot of things, that we manufacture. Now I'm going to talk about what the engineers will do in this environment. As you can see here, the engineers are the people who are working behind to really get all those product lines to life. So how engineers will start any project or anything, any new product? So in general, first you study the market, you study what you want to do, what you have in standards, what's the design parameter, what you need to do, and then you start designing. You come up with a design, second design, third design, and then you try to make a prototype of that design. After you make prototype, you have to verify if your prototype is really good. How you do that? By doing a lot of testing. When everything is good, you release your product and start selling it to the customer. When the customer gives you feedback, then you are really validating your design. Then you really know if your design is good or not good when you send it to the field. And now, after you have the design ready, it's not really ready for mass production. You made a few prototypes doesn't mean you can make thousands of it. Now you have to develop process, or you have to develop the how you manufacture it, and how you make it in a repeatable way. Don't forget that you know what's going on, but the operator on the machine, he just push the button. So you should control everything. By everything, that means you have to choose the material, the specs of material, exactly what you want it to be. You have to have the procedure, how to go from step to another step to the step after that. Process steps, do you need to heat it, treat it, for example? You have to shot peen it, you have whatever process you need, you have to have exact specs. So people will follow exactly what you say. And you already passed all tests, you lock down everything you did. Then you have to choose what machines you have to buy, or if you have it, how you want to equip your machine to do it. After that, you have to work with planning and buying, to buy the raw material, to buy all the things that you need to make your product. Then you start marketing. Marketing people will start, soliciting for your product. And you go and train everyone in the company about your product, from machinists to buyer to salespeople. Everyone should know about your product. Now you have all the facility ready to start producing your product. Now the end of R&D department is done, research and development, and then manufacturing will take over. And again, don't forget, company like this will have quality engineers, will have manufacturing engineers, process engineers, they all work together. But the one in R&D or research and development will lead everything and lock down everything, then will hand it over to manufacturing and quality, so they follow exact specs as they manufacture the products. Okay, now as we are working, we have a lot of software that we use to help us in design. There are some of the software. I'm gonna talk about them as we go, mention what those are. So first software that everyone uses, very popular, is the Solidworks. I know a lot of you use it, that software. It's very friendly, very quick. For simple parts, it's easy to really run it. Even you can do stress analysis. This is a sample that we did to train some people, where you can put all the parts, all the components, so everyone will know what you have for this one here. Now, other software is called ANSYS. ANSYS is very good software, and it's widely used in aerospace as well, because we can do stress analysis on that one. So stress analysis, you can see the stresses, you can see the movement. So when you design something, you need, before you make prototype, to make sure it's good. So you try to apply the forces, you try to see, how it's going to work virtually on the computer, so you do simulation to whatever you have in the actual life, and then see what stresses you're getting, what displacement. You go modify the design again, redo stress analysis again. When you are happy with what you see on computer, then you start making the actual part, and then you really test the actual part. So even stress analysis is good, doesn't mean you should not test it. So you do stress analysis first, and then you develop the part, make prototype, then you test that part. But here can save you a lot of time by knowing upfront that, oh, the design is good, it's not good, I can modify it, instead of just depending on making prototype and testing it. Here's another example that you can use in ANSYS. You can see the displacement deformations that can get on the parts that you are designing. Here you can see the stresses on it. Here is another software that we use. It's ElectroMagaWorks. And this one here, it can do electrical and heat analysis we now using LS Dyna from ANSYS. But this one, as you can see here, you can see, oh, the cable was very hot. As it gets to the barrel, to the pad, it becomes much cooler. And this is important, you know, upfront that, okay, my fitting will run cooler than the cable, and that's what you want. So that's good to really do the analysis first. And here's another thing, that electromagnetic field. You can see if you have two conductors close to each other, how the current will be running. And as you know, the current will run on the outer shell. And since here they are close, you see them, you know, pushing each side outside. And here, when you have good distance between each other, you see they are running, you know, nicely in a very symmetrical way. So these are also will help you a lot when you are designing. That doesn't mean actual test will be exactly like simulation, but most of the time will be good, especially if you do a lot of simulation, a lot of testing, then you know what you read here, how it's gonna convert in the real life. Other things that you may do, some customer will come with a new design. They have a need for specific things. This customer, he wants to have a specific angle, big spans. Then we came up with some design, so you can discuss it with the customer, see how we can solve his solution. You know, because you always have a problem in the field, you try to come up with a solution. You came up with a simple solution based on whatever product that you have or component. And then you do stress analysis based on this, you know, this example, you know, they showed us how the bus is spanned and what the loading will be. Then we did all that analysis before we make the part, because there's no way to go and actually test it. We have similar components. We know it's going to work. Then we'll double check now using the computer that it's going to be good. Also, we do a lot of testing, actual testing. And since this product is mechanically should hold the cable, especially in transmission lines, sometimes the tension will be up to 100,000 pounds. So that's a lot of load. So you have to make sure you can hold the cable. And electrically, you have to make sure that the electrical contact will be good and will survive over the life of the connector. And the life, usually, it's about 20 years. So you have to make sure that your connector will last 20 years. So what kind of tests we can? Here are the list of a lot of tests that we do. Tensile test, sustained load test, shift test, freeze thaw test, you know, you freeze it, you thaw it, you know, corrosion test sometimes, you know, you do all that one. Here are some of the tests that we do with some examples. So this one here is they use it for safety equipment. You hang safety equipment on it. If there is a fault current happens, so the worker will not get hurt. So they'll ground all the electricity to the ground. So basically we run in this test 85 kiloamperes and then make sure the fitting will not fail. And very high amperage, you know, current, you see how you see the cable will be glowing in red, about to fail or melt. So we have to withstand that. You have to have good cross section. You have to have good connection. So this is one of the tests that to make sure that you are good. Other tests is like mechanical tests, like here are tensile tests. So here is the fitting with the cable inside it. The pad, you try to pull it up, you know, here while you are fixing it to see how much load it can take. Here is another bus connector. You do tensile test on it. This test here to the right is called heat rise test. So we heat it to 100% of whatever the cable will be running at. Then we increase it to 125, then we increase it to 150%. And every time we take resistance, making sure the resistance and the temperature is not higher than the conductor. So this is very important to give you indications that this is good enough or not. Here is another test. It's called sustained load test. So you hang the connector with the cable and tension it. So if the connector is supposed to take 30,000, you tension it to 20,000. And you leave it for a week. And then after a week, you see, is there any slippage? Did the resistance change after you put it like that? If not, then the fitting is good. To the right, this is what we call it current cycle test. So you heat the fitting to almost 275 degrees Celsius, and then you cool it down. You heat it, you cool it down to simulate the life of the fitting over 20 years. And every time you take the measurement of resistance and temperature, if it is stable, that means the connector is good. And here in this example, you see this is a control conductor is running at 275 degrees, while the fitting are always about more than 100 degrees cooler. and you see it's kind of stable. So that's good indicator that, okay, this fitting will survive for 24 years in the field. Here is another test, they call it corona. So at high voltage, the fitting will start shooting electricity, and that's what we call it corona. And this corona will interfere with the radio waves, with the signal from cell phones. It's not good at all. So what we do, we keep, now for this particular example, we have 500 kilovolts. 500 kilovolts. And then you start shooting corona, and then you start bring it down until you don't see corona at all, and that's what you rate your fitting for. So if it's going to be running at 500 at 230 kilovolts, you have to make sure your fitting can run at that voltage. Now, other thing here is the test. You try to really, every time you come up with a test, you have to simulate the real life scenario. Here we have a fitting that will go through the roller on the tower. So we came up with something here. You tension the cable from both sides to simulate how much tension it's going to have in the field. You put the pulley or roller or the sheave, and then here you take the fitting, go over that roller back and forth, and every time you go and measure the resistance to see is there going to be any change in resistance or not. Here is the test, actual test that we did. And you see that's the setup. And this is the fitting going over that roller, because that's how they install it in the field. We have to make sure that it can survive as use it in the field. You see how it goes back and forth? And then we take it back and see the resistance of that. How is it in the real life? This is the real life installation. That's a fitting, and that's how it's going over the roller. So basically, you try to see how is it in the field, and you try to come up with setup of tests that simulate what is in the field. You cannot simulate it 100%, but you do your best, and then you go and do the testing and have the test more severe scenarios than what you will have in the field. Because here, as you can see in the field, it will move, so it's flexible here. It bounces, so it have less stress on it. So you come up with more severe thing in the lab. This is fixed, so it add more stress to the test. So you have to come up with a test with the setup, and then you test it to qualify your fitting for whatever you need to do. And again, I told you, like, whenever you are designing, you have to always come up with a drawing and all that. And this is not the only thing we use. We use also software called J.D. Edwards. Now, this one here, we call it Visual Build because you see it. And there is other software is when they take all this one and put it in the system. That software will know everything that you have in the warehouse and everything in production. So let's assume you want to make this head assembly. You put an order there, then the software will tell you, oh, you have this yoke in the warehouse, you have this end plates in the warehouse, you don't have this die block, then they issue an order to make those die blocks, right? And they have prices, they connect the order from the customer to the order on the floor to planning and what you have in the warehouse. So that's very important software. Everyone will use it, and everyone knows what we have and what's in production and what we need to produce to make the assemblies that we need. And again, I told you, you have to come up with a process, what each step, for example, for this yoke, you start with a block, you mill it, you drill the holes, and you cut it using wire EDM, and then you go and heat it, treat it, for example. All those things, you have to specify to do it. And all those steps can be in J.D. Edwards software, we call it router, how the order will move from one stage to another. Other things that we'll be dealing a lot as engineer is a material. For example, we have different alloys of aluminum. We have like 6101, we have 1100, we have 6061. Each one has different conductivity. Each one has thermal conductivity is different. So you need the strengths, you have to decide what you have. Also, when you work on tooling, what alloy you want to use for every component that you have. So you have to study those alloys. You have to be very good. If you have a failure, you have to know metallurgy as well. Always you can have consultants help you. You can send it to the lab, but you should also know a lot behind it. So you always have to educate yourself about new alloys, about new processes, about heat treatment, about everything you'll be working on. Other things that interesting, working engineer, you always come up with some papers that have some solutions. So here, for example, we wrote a paper. It's a joint paper with the lab. We did like a special test we came up with, and we present the result of that test, and we recommended all utilities and the standard to adopt that one so they can test it in future because we saw some value in it. So this here, me and my co-worker working with Connectrix to that one. Other things that you always have to keep in mind that whatever you do in new ideas, creative ideas, you have to patent it. So you have to deal how to do the patents, how to do all things, because now you are also working, but it's the company should protect itself. So you always have some kind of new products, proprietary products, information that you have to keep it. So here is one example of patent we filed for the company. And here is another patent, just an example what you do. So that's other things that you always keep in mind that you have to do as you are working. Other thing, of course, we do the drawing, and I apologize, I cannot show any drawing, because nobody's supposed to see it. I cannot show you actual process or actual router because I have proprietary information, but you know how to make drawings, all these components, for example, each one should have its own drawing, dimensional drawing, we call it, where you specify all the details of dimension, all the material, all processes, everything that you need to make it. You have to have it on that drawing. And this one is kind of assembly drawing, so you can know how to assemble this part in general. So that's in general, what we do here. Why we do all those testing? Always safety is first. Safety of people, safety of nature, safety of everything. Like, what happened, one connector failed at PG&E in San Francisco, like almost 90 people died, were killed in the fire, and all the forests were burned, cities were burned because one connector failed. So you always have to really have safety. You don't want failure because a lot of fires, a lot of people may get, killed or, hurt. And you want this product to live for a long time without issues because there is a lot of economical reasons behind that one. And sometimes the connector is in the middle of the forest, in the middle of nowhere. So until you know where it is to go and fix it, it's going to take a long time. So that's very important, to keep in mind whenever you are designing or coming up with any new product. Here are some of pictures of people are installing it. They are switching it now, holding the tool. The tool should be safe. Imagine this tool will fail, that somebody can get hurt as well. They are connecting it. Here is they are doing work on transmission line. You see how high they are, like, it's very high, on the towers, connecting it. And sometimes they use helicopter to do the installation where sometimes they cannot reach it, especially in forest, in mountain. They can, do the installation using the helicopter. Yeah, this is in general what we do and, how we do things, And as I said, it's engineering and developing. So not if all your time is going to be just developing a new thing, coming up with a new thing, sometimes maintaining, improving the design of existing things, and sometimes it's really, coming up with in new or investigating things, investigating failure. You always have something to improve on the study. So that's why it's always exciting when you are an engineer, because you'll be exposed to a lot of things, and too many things you can study, you can learn. It's you spend your life learning, and sometimes you enjoy that. It depends again on the person and the passion and what he wants to do in his life. And again, if you have any question, any concern, you can always contact me. Here is my email address. And if you guys would like to really visit my company after COVID pandemic is over, you are welcome. I can arrange that and definitely invite you to lunch after that. Well, thank you guys again for inviting me.
Thank you, Mr. Khansa, for that thorough presentation. You can stop the screen sharing right now if you want. And now our chat is going to be open to questions from the audience, so please list any and all questions you have. I will be moderating it. But in the meantime, we're going to ask you a question from our prepared questions that we asked the team earlier on. So our first question is, how is your work-life balance?
Work-life balance. It's a good question. So, you have to be physically 8 hours at work. Sometimes you have to meet deadlines. Sometimes you have to do testing. So you have to stay more than, 8 hours. Sometimes you have to travel like for a week or a few days to do testing. Sometimes you have to go and meet with your customer, with a client to solve an issue, to discuss a new product. So you always, in my job, you have to travel. You sometimes you have to stay late. Sometimes you have to work over the weekend. But sometimes you enjoy that because again, when you do testing, traveling, sometimes it's enjoyable, but that will put more stress on the family because sometimes you are not at home, you leave your kids, you leave your wife. So sometimes it's not the best. So always, that's why whenever you are applying for engineering positions, they will tell you there's travel 20%, there's travel 50%. So up front, and you can tell them, yes, I'm willing to do that. No, I'm not willing to do that. And some people, not everyone will travel. If you are in charge of products that you need to really do traveling, you do to really stay late, you always, expect that. But in general, engineering, you have to get your project done. So whether you finish it in a couple of hours or you have to stay overnight, you have to finish it. You have to meet the deadlines. If they have emergency in the field, you cannot just leave them. Oh, okay, you have emergency, it's not my problem. I'll see you tomorrow. I'm going to sleep. You cannot do that. So sometimes it's stressful, but most of the time you really enjoy it. You'll not see it, but it may put some stress on the family as well. But as an engineer, you enjoy because you always have something to do and something new to challenge you.
Thank you. Now we have our first question from the audience. This question is from Don, and he asks, how long does a typical testing phase last for like a certain material or building, etc.?
So there are a lot of type of tests. If you are doing tensile tests, that tensile test can be done in 5-10 minutes because you are just pulling it until it fails. Some of the tests that we put, like to do the corona testing, you start increasing the voltage until it reaches, let's say, 500 kilovolts. And that may take like 15 minutes, 30 minutes to get there. Some tests that I showed you that you heat it, you cool it, it may take 6 months to 1 year. You're still heating it, cooling it, heating it, cooling it. You keep monitoring it and seeing, and that will take forever. Some of them that we do vibration, 10 million or 100 million vibrations to really simulate how it's going to be in the field. That will take also months. So a lot of tests here because what you want from the test. Now I want to simulate the life of the fitting, and that will take forever because just heating, cooling down, it takes a few hours to heat up. You have to leave it 2 hours at that temperature. You have to cool it down, it takes 2 hours. So every cycle to really do the setup and have it automated, so because they are programming it, they are setting it up. So this is like fun, usually doing engineering. But that will take like a couple of months to do. So some tests will take a lot, like corrosion test. You put it in fog test or salt spray test, they call it. You put it in a chamber and you have a lot of fogs, salt fogs. And you have to leave it like months or two to simulate the real life of, let's say, 10 years or 20 years to simulate the coastal area. So some of them, they really take long time, and some of them are pretty much fast. But the process is not only when you just put it on the machine. Until you get there, you almost done a lot of things. You did a lot of testing, a lot of prototype, you did a lot of verification. And then when you want to qualify it, then you do the final test and you document it where you show everyone, hey, this is the final official test. Then that seems maybe it'll take, for example, tensile tests, 10 minutes each, but the work behind it, you'll be working on it. Some of the projects like more than a year, 2 years, 3 years. Depends how complex is it in you, not in you, existing little modification. It varies.
Okay, we have another question from Don, and he asks, would you say that testing in other fields, I'm assuming engineering, is faster or about the same time frame?
Well, it depends like what testing you are doing. Like, let's say, for example, any part that you make, has to be tested. Now, over time, testing will become less because you have a lot of data about testing. But everything you finish, you have to do testing. whether SpaceX is testing its rocket, so they have to go and launch that rocket. It fails, they have to make another one. It will take them a year to make another one. Then they try it again. So that program between testing and go back, making sure the design is good may take years. It depends. Sometimes you are designing something very simple, like simple beam. You go and test it, that's very fast, So it depends. Sometimes the design is very simple. You are designing component, you want to test it. And sometimes you have to come up with a new tool and you have to test it. Coming for a new tool just to make the prototype, sometimes it takes 6 months because you have a lot of process. You take it, you send it to heat treating, it takes a couple of weeks. You send it to shot peening, it will take a couple of weeks. So there's a lot of operations that you have to take time. And this is also one thing that you have to be good at is managing your project. How to start from A to Z while everything is moving, you have timelines, you have to keep it, dealing with your vendor while you are doing other projects. So you don't do one project and wait until the prototype comes back. No, as you are doing your project, there's another project at different stages, there's a third project at different stage. So you always have to manage, and these skills, as you work more, you have to gain it so you can manage your work, or your project. But again, every test, you always have some kind of testing. And again, at some big companies, they have test engineer. His job is just to do testing. Some people, his job is just to development. Some people just for material. The smaller the company, the more you have to be exposed and doing more things. So if you are working with Boeing, you are working with very specific, narrow things. If you're working with much smaller companies, then you have to do a lot of things.
Okay, we have another question from Mr. Shaheen, and one of our panelists yesterday, and he asks, how important was your master's degree for your career advancement?
Okay, here is the deal. Now in these days, specialty become very important. Now engineering is very broad things. Mechanical engineering, too many things under mechanical engineering. Aerospace, making turbines, for example, making thermal station, making engine, combustions, rockets, connectors, plastics, a lot of things, under engineering. So when you go to master, you see I'm specialized a little bit more in this field. Now, that will limit where you can work because now you are more specialized. Like when you go to a doctor, that doctor is specialized in specific things, that all what he does is that specific thing, but he's very good at it. So nowadays you see it's very important to really be more specifically specialized in one field. I'm not like engineering everything. I'm specialized in design and manufacturing, And the other thing that you get from masters, master is slightly different. Masters and PhD slightly different than bachelor, because they will give you more tool of how to research things, how to come up with a solution. So you get the theoretical skills of how to do things. And when you are really working, you know how to really search it, how to find solution, how to come up with a new thing. So that's get you a more refined skill to really be better in being analytical or, problem solving. And these days, it's a plus to have a master, but you don't need to really waste 2 years for master, because companies will not consider 2 years as a 2 years expertise or experience in the field. It's better to get your bachelor, start working, and then either you take a year off to do your master, or you do your master as you are working. Now, if you are planning to go to PhD, then in that case, don't recommend to work, just go straight, because you'll end up being a researcher, not an engineer. Researcher in engineering, not really actual engineer, in the field. I hope that answers the question.
Okay, we have one final question, again from Don, and he's asking, what is the difference between verification and validation?
Okay, so it is somehow the same. Talking quality-wise, when you do, for example, ISO audit, or whenever you are talking quality, verifying, that means you verify your project is good, the design is good, it will meet the requirement. But when you validate that it's really good, it's when you send it to the field. So basically, it's both verification. One is you verifying in the lab, where you have everything controlled, and the lab personnel and yourself will be judging it based on some standard or written standard. But then when you send it to the customer and they go actually and install it and play with it and see all the issues and tell you, yes, your product is good, it's validated, called validated. If it's not, then, your project basically is useless. Whatever you did in the lab or all the, testing you did, it's good, doesn't matter. If it's in the field, it's not good. So always they distinguish between that. You verify it yourself in the lab before you launch your product, and then when the customer starts buying it and give you the feedback that it's good, then that's validated.
Okay.
And again, one more thing I would like to add, maybe not mention it, is that as an engineer, you are not always just researching unless the position is researching. It's not all the time you are developing unless that specific title. Most of the time you have to maintain existing product that you have. So that will take some of your time per daily work. And sometimes you have to support other departments like manufacturing. They come up with issues. A buyer will come to ask you, the warehouse guys, the quality guy. You always have to help other departments. That will take some of your time. And then you would have some strategic projects that will take a year or 6 months or whatever you'll be working on. And then you have very little projects that can be done in a few hours. You can do it or a couple of days. So you always have a lot and you have to manage all that. It's not like only doing one thing. But again, the bigger the company, the less that you'll be doing. For example, my position is just to do stress analysis. I don't do anything but stress analysis because the company is very big. Everyone is doing only one thing.
All right. Thank you again, Mr. Khansa, for coming and telling us so much about mechanical engineering. I know I learned about testing from your presentation. Right now, we will be heading into a short break before going into our second panelist, so stay tuned for that.
Okay, thank you for having me.
All right, and we are back. So now to introduce our second panelist of the day, we have Mr. Eric Gever. Mr. Eric Gever is a systems flight engineer at Boeing, and he has 13 years of experience in space-based technology and design. Today, he will highlight how these technologies help solve sustainability and environmental challenges on Earth, ultimately improving everyone's quality of life. So please give a warm welcome to Mr. Gever.
Hi, everybody. Thanks for having me today. So I'm going to share my screen here and show you my presentation. As was mentioned before here, I'm an aerospace engineer by major. My actual job description is actually a flight systems engineer. I want to explain what that means in context to aerospace engineering and how we interact with all different types of engineers in my industry. So again, I do work for Boeing. I work in Seal Beach, California here. I also want to talk a little bit about how spacecraft and space design has a huge impact on everyday life here down on Earth, and how that really impacts and can really support improvements to the environment and the climate and all sorts of things. So just to give you a little bit about how I got started and interest in engineering in general. Well, I was actually in FIRST Robotics as well. So you see back when the early 2000s, 2001, 2002, I was actually a high school student, just like the students of Poly Robotics, doing my own team. I was actually on team 204 of Viking Robotics in New Jersey, and competed on that team for a couple of years. I, of course, got inspired to learn more about physics and math and engineering and things like that from that high school experience. Unfortunately, after a couple of years being on robotics, my family moved to a different location in New Jersey. The new school that I was in as a junior and senior did not have FIRST Robotics, but it opened up a breadth of new opportunities for me, including some other smaller engineering challenges and engineering specific classes that got me even more interested than before, and specifically like aerospace and computer science and computer engineering. So I kind of established a little bit of a baseline in controls and computer engineering in high school, but wanted to expand myself a little bit and learn an area that I really didn't know too much about quite yet, and that was the area of aeronautics and astronautics. So I went to college at Rensselaer Polytechnic Institute. I'll show you more about my history there, but wanted to show you a few different projects I worked on during that time. You can see some more on the top right here. This is me working on a robot, the controls portion of it, back in high school. The top left there was my involvement in Design Build Fly, which was an engineering competition that I participated in when I was at RPI. And also, met a lot of folks who ultimately joined me in the aerospace industry. I was part of another competition called the LITEC Balloon Control Challenge, where we were working on, a blimp-based control. And so through these projects, it kind of got me really interested in, just learning more about how, aerospace works, and so kind of took it from there. So anyway, a little bit about my career and some of my out of career interests. So back from 2004 to 2008, I was an aerospace mechanical dual major at RPI. That was my undergrad. When I was an undergrad there, I ended up getting an internship at Boeing in El Segundo, California, which is what kind of kicked off my career in general. I went back after my internship my senior year, finished off the schooling there, and ended up going almost straight back to the same group I was in as a full-time hire. So I started in Boeing El Segundo working on commercial spacecraft, commercial satellites. So you can see there the 702 SP is one of the major large platform spacecraft. The panels there are actually the size of a football field, to give you a sense of scale. They're really, really huge satellites we're talking about deep in space. Not too long after that, I actually moved down to Huntington Beach, California, where I worked in a group called Experimental Systems Group, and that's where I worked on the X-37B space plane, which at the time was a brand new concept, kind of a miniature space shuttle. And so those types of flights are still in effect today, which is pretty cool. While I was at Boeing at that point, I got a graduate engineering degree at USC. One of the benefits of working for a large company like Boeing is that they'll actually pay for you to go to school and get your grad degree. So what a lot of people do is they get their undergraduate major and they graduate, and then they go into their company, and their company actually helps them helps them get a master's degree. And that's really helpful. Of course, there's a lot of time involved with that. Working full time as well as working on a master's can be, pretty time consuming. But once you get through it, it's pretty rewarding, because there's a lot that comes from having a master's in aeronautical engineering. But not only that, you get to I find it to be very interesting, because unlike undergrad, you get to really specialize in the specific types of classes you're interested in doing. And so it really helps supplement the job you do every day. In 2016, I ended up changing jobs and went to Harris Corporation, now known as L3 Harris. So they were actually based in Rochester, New York, but I worked on a government project in Virginia. So I was kind of remotely working with a lot of my colleagues at what we call the factory up in Rochester. I was kind of the representative support there, but what I did was I was a senior payload systems engineer. And so we were designing the integration between our payload systems and the bus, or the main part of the spacecraft for a major government customer there. So that lasted a couple years. I then moved on, still at Harris, worked in Florida for a little while, working on what was called HSAT, which was a demonstrator for CubeSats, actually. So Harris was newly getting into the the full end-to-end spacecraft bus environment, and I was helping them kind of kick that off and getting some smaller size satellites launched into space. In 2019, I decided to actually come back to California and come back to Boeing. So right now I'm a lead systems integration engineer. I'll talk a little bit about what I have done over the course of these different flavors of engineering. And I currently work on proprietary projects. Unfortunately, I can't talk much about what I specifically do project-wise right now, but I find it to be very exciting. I find myself, wanting to go into work every day, because it's just so fun to be involved in, such exciting projects. So that's really the kind of the goal of your career, is to find something you're really interested in and know you can make a big impact on. So I really do enjoy it. Other than my regular day-to-day work, I have quite a few hobbies that are very engineering related. As you know, I'm a FIRST robotics mentor. So Poly Robotics is certainly not the first team I've mentored. I've actually mentored about 8 or 9 teams now, starting when I was in college, a college mentor, going all the way through being a new hire at Boeing, and started a few teams in the Orange County area. So I've been very involved in FIRST robotics mentoring. Personally, I also perform high-powered rocketry, so I have a certification for high-powered rocketry. That's a rocket I launched off about 1.5 years now. I'm actually building another one right now. I've competed on BattleBots, so I've actually competed with 2 different teams. I was a team member of Duck in 2019. As you can see there, I was kind of the main pit crew member, and basically was responsible for getting the robot maintained and ready for the next fight. I also competed a smaller extent with Blacksmith, and helped build some of the support armor for some of their matches, just to kind of get my feet wet in the BattleBots arena. Other than that, I do a lot of competitive drone and wing racing. I actually travel around the country right now competing in drone races, which you build your own drones or wings, and you fly and race them against competitors across the country. So I have a lot of fun doing that, and get to apply some of my engineering skills in that area. And then some other things, I'm really into hiking and caving and canyoneering. You can see me coming down a rope here. Canyoneering is a very technical and niche hobby, where basically you're descending down waterfalls with ropes. And so you have to learn a lot of like rope management and gear management. And so to me, it's, it's a pretty structured and thought-provoking type of hobby that you can get into that's also physical in nature. So that's a little bit about me and what I've kind of done over the years here. A little bit about what a spacecraft flight systems engineer does. So 3 little main topics here that I wanted to talk to. So the first one that I've done a lot of is called ConOps design, or mission concept of operations. So what we do there is we're planning out the day in the life of a typical spacecraft, what we call the diddle operations. And so we're basically designing, how does the satellite communicate with us on Earth? How does it activate its sensors and its payloads to actually carry out the mission it needs to carry out? How does, we might need to, for example, bounce signals off of another satellite called a data relay satellite in order to hear it back at our ground station. We design, how do we activate it? So once we launch, how do we actually get the computers and the systems up and running and communicating with each other and set up our fault management, just in case something goes wrong? How do we perform those kind of switchovers between different computers? And then end of life. How do we dispose of the satellite when it reaches its end of life, which is typically when we've run out of propellant, so we can no longer control the spacecraft. After 15 years or more. How do we deorbit it? How do we send it into a higher orbit that will ensure that it won't crash into any other satellites? When we want to put a new one up that has new technology in it. Another thing we do is called payload and component systems integration and test. So there, what we do is we actually work in labs and we actually put the spacecraft together and test out all of the connections to it. There's a lot of different methods for data transfer, and of course, when all these, when you're combining a payload with a bus, you have all sorts of sensors and things like that that have to be connected correctly. And so we make sure that all of the hardware is both connected correctly, that it's going through the correct set of testing, like thermal vac chambers, vibration chambers, acoustic chambers, that kind of thing. And that we understand the results of those tests and build test reports and summaries, things like that. And then we also make sure the software, both on the spacecraft itself and the simulation software that we use to test our concept of operations, is well in sync, in that the things that we're testing on the ground is what we call test like you fly, or will behave the same way once we get into space. As it turned out, as I've learned over the years, sometimes the test like you fly scenario, it's a lot more things go wrong on the ground with our simulators than they do on space. Like, our real life hardware is better behaved in some cases than the software that we try to use to simulate it on the ground. So sometimes you have to kind of figure out, is that a real response that we're getting, or is that kind of a signature of our simulation environment? We can't emulate the temperatures or the pressures of space on a typical test. So we have to kind of pretend and hope that the simulator that we built is representative of that. And we try to do the best job as possible. And then another part of this is the ground system design and flight operations and the mission control environment. So in this case, you work with, in some cases, directly with the operators, the ones pressing all the buttons. Giving them new procedures, explaining how to perform certain things in space. When something goes wrong, we have what's called an anomaly event, how to recover from that. And so we form these teams of engineers that come together and just solve problems and think about it. How do we recover from this problem? How do we switch over to redundant units, or maybe use a procedure in a way that we didn't anticipate using it for, in order to carry out what we need to do? And so we work closely with our ground teams and our ops teams to understand the spacecraft's behavior and react to it in a reasonable way. Of course, there's also designing of the whole ground mission system as well, including like how maybe the customer might ask us to carry out some sort of procedure, how we actually do that, right? And it's a combination of like scheduling different types of procedures over the course of an orbit, figuring out what different types of activities like maintenance and things like that won't interact in a negative way when they're run at the same time. We send commands up to the spacecraft, knowing the timing is really critical of that, and how the different commands might interact with each other. So that's kind of what we do as a systems engineer. We put it all together and figure out how exactly to make it work exactly as we need it. Again, a little bit about my space project experience specifically. So when I was on 702 HP, I was working for Boeing Satellite Systems on SkyTerra and MSV. So these are the actual spacecraft that I've been involved with. When I was there, I was working on flight and controls and autonomy. Autonomy, you can kind of think of like autonomous mode, but it's effectively when the spacecraft is doing its thing on orbit, if something fails, what do we do to recover? Do we switch over to redundant systems? Do we point the spacecraft towards the sun to make sure the batteries stay well charged? Maybe we point our antennas to a ground station. Generally the operators of the spacecraft might not know too much about the entirety of the system, so they come to someone like me to help figure out what went wrong and what we can do to solve it. Again, when I worked on the X-37B, I did a lot of comps design and recommended operating procedures, as well as the systems integration for that, including like experiment integration. 702SP, again, back on the commercial satellites. So this was kind of a fleet of spacecraft that Boeing was developing, kind of like their, like a 787 fleet or a 737. We're actually building production lines of the 702SP spacecraft and then selling them to potential customers. So, you can buy an aircraft off the flight line, you can buy a spacecraft off the flight line, same thing. Again, proprietary project at Harris Corporation, where I was also doing vehicle engineering and payload integration. I mentioned before the Harris CubeSat called HSAT, and now work in Boeing BDS as a proprietary program lead systems integration engineer and work on ground systems as well. All right, a few skills that are required in flight systems engineering and aerospace engineering for that matter. The big one I consider for anyone, especially a new hire coming in that would work with me, is problem solving skills. Seeing that someone has the ability to analyze a problem, brainstorm different solutions, understand their effects and implications, and apply their knowledge and experience to kind of make a recommendation to how to resolve it. So they might not necessarily need to do calculus or some sort of trigonometry or know some physics equations. They just need to know how to approach the problem and maybe use math as kind of a tool here, but ultimately problem solving skills are the big one. Communication and teamwork. So it's important to be able to work with others as a team. First Robotics, of course, is a great primer for that, but being able to work with different technical backgrounds basically every single day is really critical. Having an objective and good high-level understanding of the environment of interest. So in my case, I'm a space person. I need to know how orbits work. I need to know how the space environment can affect our satellites, how things get really hot in one place and really cold in another place. How computers can interact with sensors, that's the kind of control systems, and how to build redundancy into a design. And of course, having some skills in actual software like MATLAB, project management tools. We use what's called STK, which is Satellite Toolkit or Systems Toolkit now. Excel, spreadsheets are pretty commonly used in aerospace, so just be familiar with spreadsheet manipulation because they will help you. Programming and scripting, and again, a little bit of math and science skills there. So let me talk a little bit about space technology and the environment. So a lot of people ask me as an aerospace engineer, like why we actually bother going to space in the first place. I hear this time and time again. People say we have enough problems here on Earth. Why should we be spending all this money on space? Why does NASA have a budget right now? My answer to that, in all cases, is that sometimes the best way to solve problems is to first get a better view from above the Earth's surface. And I want to show you some examples of why I think it's so important that we invest heavily in space travel. So a few things about just real quick what satellites actually do in space. So to start, we'll talk about things like navigation. So you buy GPS or you have GPS in your phone or in your car. People take it for granted and think it's just your unit, but in reality, I mean, this is a network, a large network of satellites that have very precise timing and are helping keep us knowledgeable about where we are in the world. And GPS is the one that you're pretty familiar with. GLONASS is actually the Russian version of it, and I believe China has a new one as well. So does Europe. But these navigation satellites use very precision timing, and it's actually the difference, thanks to general relativity, the speed of light, between the different satellites that tell your GPS unit where you physically are. So that's pretty cool how that actually works like that. Data relay. So data relay actually helps us transmit data across different parts of the world. The world being a sphere, it's impossible with regular links unless you have a really long wire or go through the Earth, I suppose, to actually communicate with other countries across the world. But thanks to data relay networks, that's how we do it, which is why you can access servers, say, in China over the internet with almost no latency, thanks to satellites and what they do. Of course, entertainment, folks who might not be plugged in a city environment might rely on that for their TV. Even around here, people do. XM radio, people take it for granted, but especially if it comes with a new vehicle, having satellite radio anywhere in the world is a pretty cool thing to have. So Earth imaging. So I'm going to talk a little bit more about Earth imaging satellites, but it's pretty critical that the types of sensors that we put up on orbit are giving us the feedback to really help understand our environment and the impacts that the environment has. And that goes around with weather tracking as well. Weather and Earth imaging are very similar in that regard. And then we have things like Earth science, where we're measuring the types of chemicals in the environment and soil moisture content, and detect changes to our climate overall. So I want to give you a few examples of some pretty recent events that satellites have helped us really understand. This is a couple of these were back in 2018. So you might have remembered a couple summers ago, there was a pretty big earthquake up in Ridgecrest in the desert. That was a magnitude 7.1. And thanks to satellite technology, we actually used the sensors on board, including minute changes in the gravity fields around Earth, to detect where the Earth changed its actual elevations, right? So because it was the nature of the earthquake, some areas dropped in elevation, some areas rose in elevation. Hard to tell just by looking at it if you go up to the desert, but satellites can easily tell you exactly where those elevation changes happen, and therefore where maybe certain areas on land are at risk for future earthquakes, or where places were impacted if maybe there was infrastructure there that that needed to be fixed, and no one knew because you don't have that many people out in the desert monitoring things all the time. Of course, hurricane tracking. So this is a cool visible and infrared view of hurricane barrier formation. This is also in 2018, imaged by GOES, a geostationary spacecraft out in the Gulf of Mexico. So we don't really have that many sensors out in the middle of the ocean to tell us that hurricanes are on their way. Of course, being able to look at the cloud moisture contents and layers and things like that, we can use these spacecraft to early warning detect who's going to be hit and impacted and save lives in that way. A little more recently, this past summer, fire detection was a really big thing that we were doing with satellites. So on the left there, actually detecting where the fires started in California. A lot of these fires start in remote locations, especially when it's the lightning induced sort of events. And short of having drones or fire towers all over the place, we can use satellites to very quickly detect the ultraviolet waves that fire produces and report back. And so we can tell firefighters to go directly to these locations as soon as the fires start. And it's a 24/7 sort of detection. A kind of similar technology using infrared light. You can look at smoke travel from those fires. And so these are two different sensors measuring different things. In this case, we're looking at particulates in the atmosphere, which can help give warnings to folks about where folks with asthma might have more trouble because of the amount of smoke, and kind of gives folks a heads up if they know smoke is coming their way. So from an environmental standpoint, satellites are really critical to giving us warning, giving us kind of detection all over the world, and knowing what's going to happen so we can respond to it and help save lives. A quick thing about where satellites actually go in space. So if you're not too familiar with spacecraft, you might, of course, be following SpaceX launches and things like that, or trips to the space station. But we have on the order of like 6,000 spacecraft actively in space right now doing all sorts of things. Thanks to SpaceX, I think we have like an extra 1,000 or so recently with some of their new satellites. But the three different areas that we focus on from an Earth standpoint, or Earth orbiting standpoint, is what's called LEO, that's low Earth orbit. that goes from about 200 to 600 kilometers altitude. That's where we have all our human space flight, like the space station. That's where we do a lot of our Earth imaging types of things. That's where CubeSats, maybe a university CubeSat launch might send us to. Space telescopes like Hubble is in LEO, as well as the large constellation ComSats like SpaceX's Starlink or the Iridium network that we use for cell phone coverage. This is called a ground track down here. This is actually how where the spacecraft is actually going over the Earth. And imagine that this flat-looking Earth was a sphere. This would actually be a straight line, but the way we actually map it in ground track makes it kind of look like a sine wave or a curve here. That looks a little bit different when we're talking about MEOs or medium Earth orbit satellites. So GPS is the most common user of a MEO. And the reason we need GPS to be up there is because when your satellite device, your GPS device, connects to a satellite, it needs to kind of lock onto it and stay with that satellite for a while. So these satellites will generally be in view for close to 12 hours or so. And you have to see many of them, at least 3, but ideally like 7 or 8, to have really precise knowledge of your position on orbit. Those still look like a sine wave here, but they are over a much larger area here. And then geostationary, so I've worked on these as well. And so geosynchronous Earth orbit is at a very specific location. It's at 35,786 kilometers altitude. And the cool thing about that location is that it actually keeps the spacecraft above the same point on Earth all the time. So as the Earth is spinning, the satellite is spinning around the Earth, but because it's matching the rate of Earth's spin, it actually stays in location relative to us looking up there. So most of our entertainment, like DirecTV and XM, data relay satellites, weather satellites, are all at geosynchronous Earth orbit and are specifically sitting right there. When we look at a ground track for that, it actually kind of looks like a figure 8 of sorts. The reason it's a figure 8 is because they're not always necessarily right at the equator. It's not usually ideal to have a spacecraft always sitting right at the equator because maybe we want to see more near the poles. So it's going to go up and down in latitude as it orbits around the planet. The reason that it's a little bit longitudinally like this is because we can never keep it perfectly right at 35,786. It might be a kilometer higher or lower. We do what's called station keeping in order to keep it close to that, but it'll always try to tend to verge off a little bit thanks to the moon's gravity and things like that. So the closer we keep it to like a point in space, that's the most ideal for that kind of orbit. So, why do we actually want to go to space and do all these things there instead of investing in funds here? Well, to me, engineering and innovation is kind of a result of necessity in many ways. When we think of a new engineering project to work on, a lot of the time and effort and money is spent solving problems. It takes a lot of time and money to solve those problems. And to motivate folks to do that, sometimes you need to present yourself with a very challenging environment first in order to accomplish those goals. And space, in my mind, is one of the most challenging environments because basically you're sending a spacecraft up that will be unserviceable for 20 years. You have to make sure that no matter what, it's going to work 24 hours a day for 20 years, which is certainly a challenge. They reach extreme temperatures. You can have temperatures that are as low as a few degrees above Kelvin, 0 Kelvin, all the way up to say 300, 400 degrees Celsius if you're keeping something in the sun all the time. So as a spacecraft engineer, we have to design, how is this thing going to be orbiting the planet and rotating if necessary to heat it up and cool it down in different places. How will different materials heat up at different rates and cause bending and changes to the structure? We're exposed to high levels of radiation. So radiation can easily affect computers and make them do what's called bit flipping, basically changing the data on a computer all the time in memory. And so we have to be able to have our software resilient to that. Requires renewable energy generation. So that's a big one. So renewable energy that we want to use here on Earth has mostly been developed thanks to space technology design. And trying to get as much energy out of a small area as possible is critical for that. When we're talking about folks here on Earth, as the climate changes and the population increases, we'll see natural disasters increase in intensity. And so it's really critical for us to design sustainable technologies that will help us preserve humanity over time. So spacecraft really help us by observing Earth's climate and chemical composition, understand the trending to see what areas are effective in making improvements and what areas need to increase that work effort. Detecting our weather patterns, so we know when people are in danger from extreme weather. Observing changes in Earth's crust to understand earthquake risk, which I showed you earlier. Monitoring the oceans. It's easy to see what's happening off the coastline, but far miles into the ocean, we have no idea what's going on for the most part. So we use satellites to really have a better understanding of that. It also helps us with navigational tools, as I mentioned, and worldwide communication for instantaneous information travel. We drive a lot of design from solar and fuel cells by necessity, which is, have applications back on Earth that we can then apply them to. And one big thing is materials design. So as we try to find things that are stronger and lighter and have maybe more protection from extreme temperatures and radiation environments, all that stuff is driven by necessity in a spacecraft environment. And once all that technology gets designed, we can then use it for much more cheaper applications on Earth. So I'm almost done here. I know we're going a little late here. So why send humans to space? One, human life support design. So designing ways that humans can live in a potentially unsustainable environment would be critical once we enter areas that might necessitate that. Efficient food production, reusability of water and air. Those things are required before we get to space. So it's important that if we're building on space, we can again use that same technology back on Earth. Space travel is very expensive by its nature because it's needed for the first time on these missions. But so many things that have been developed for space we use on a daily basis here, even in robotics, including Velcro, thermal types of technologies, freeze drying, camera image sensors, like air scrubbers, solar panels. Computers, for the most part, were designed because of space travel for the most part. So it's pretty critical. And one last thing I'll say here is about going back to the moon. So many of you know that the Artemis missions for NASA have plans to send people back to the moon. A lot of people ask, well, why should we go back? We've already been there. What's the point? Well, I mean, I haven't seen it yet, of course, and neither have most of the students. Anyone younger than me haven't for sure. But there are a lot of benefits of human space exploration and lunar exploration. One of them is mining of helium-3. So helium-3 is a very rare isotope of helium that's not really available on Earth because Earth's atmosphere deflects it away when the sun, beams it across the solar system. So luckily, with no atmosphere on the moon kind of just absorbs it all. And so helium-3 mining is very critical for being able to collect it and bring it back to be used for medical applications like MRIs and such. Interstellar observation. Just recently, NASA was proposing a huge radio antenna on the other side of the moon for interstellar signal detection. The benefit of being on the other side of the moon is that you can call it the dark side of the moon. It's really RF dark, radio frequency dark, which means that all the signals from Earth won't interfere with its ability to collect from deep in space. I mentioned a lot about sustainability and our need to design new things to keep humans alive in that sort of environment. And then also enabling interplanetary human exploration. The moon itself is a really good starting point for refueling, recharging batteries, storing supplies before you might start venturing off to Mars or beyond. And so it would be really critical if we ever started getting into interplanetary travel to go back to the moon and establish those sort of things. So with that, that was kind of my little pitch there, and I think that's about it. So I will stop sharing, and if anyone has any questions, feel free to ask them.
Yeah. Thank you, Mr. Gever, for sharing that presentation. Seeing as we are a little short on time, we will only have time for a few more questions in the chat, so type away. In the meantime, we will be asking one of the questions that is on our list, and that question is, what is the strangest way to generate lift that you can think of?
So I'm actually glad you asked that question because if I can, I wanted to share a quick thing that that is actually pretty cool in this area. One sec. So this is the coolest thing from a lift standpoint. Oh, sorry. Let me just share again. Okay. All right, so we use what's called the Magnus effect in aeronautics. The Magnus effect is pretty cool because basically it basically uses the difference in air velocities to produce lift. And so one of the cool things you can apply this to are actual cargo ships. These Magnus force sails, these are actually like wind sails, but why do they look like they're spherical? Well, they actually spin. And the effect of them spinning while the wind is passing by them creates a difference in velocity between the two different sides of the cylinder here, and that actually creates a lifting force, and that lifting force will actually propel even huge cargo ships, across the ocean. Some folks have tried to apply Magnus effect to aircraft as well. So instead of like large wings, they would have cylinders instead, which take a lot less space and produce similar amounts of lift. We experiment a lot with the Magnus effect when I was in college and got to see their effects through wind tunnels. So I just think that's a pretty cool example of how you can use aeronautics in strange ways.
Wow, that's really cool. I didn't know about that at all before. Seeing as we don't have any questions in the chat, I'm going to ask a question that I have. So in your work, how important is research and development? Like Mr. Khansa spoke about it being a part of mechanical engineering, but how does it apply here?
So a lot of the technologies that we test on orbit, especially when we're talking about government proprietary programs, a lot of the reasons we want to send something to space is to increase what's called its TRL, or its technology readiness level. So as a aeronautical systems engineer, one of my jobs is to understand some of the research that's going on in space and aeronautics, and be able to help them gather their data once we get on orbit. So although I haven't dealt with that many like research, like science research types of projects in that regard, I have dealt with integrating those research projects onto our platforms in order for them to test out their concepts. And what's cool about that is once we raise their technology readiness level, they prove that it will work the way they think in space. They'll start applying that new research to actual like baseline spacecraft design. And so we work with a lot of different naval research labs, a lot of different customers both in the government and at universities in order to help basically lift their experiments to space and see the data that they get from that.
And finally, one last question for the day. This is another question from our list, and it's, what's the most valuable thing that high school taught you?
I think the biggest thing high school taught me was kind of working on a team with, especially in an engineering area, learning how to work with others, put together things when you might have a lot of different design ideas going on and brainstorming, being able to kind of objectively understand how those different ideas can interact and the people behind them, and then work with others to actually make the project successful, ultimately. So I think group projects in particular are really critical, especially for engineering fields. Group projects in which you are trying to solve a problem and come up with a solution. So yeah, I think that group work, having kind of a background in the physics and the math is certainly important to be able to apply the ideas you're putting into those group projects, but the collaboration side of things is the biggest one to me.
I see. Okay, thank you so much for spending your Sunday evening with us. And now we are going to end this career panel first by thanking all of you guys for watching, and we hope that you learned a lot about future careers that you may pursue. But before we end the day, please fill out the feedback form that is in the description of this video and let us know what you thought about our event and what future events would seem like. Once again, a great thanks to all our panelists, without whom this career panel wouldn't have been possible. Also, a big shout out to our researchers and networkers, Angelica Cagnetti and Teresa Noun, our networkers, Dawn Dow, Tori Duffy, Sean Louis, our ad designers, Lil Khansa and Pia Howe, who made the wonderful ads on our Instagram, our online livestream manager, Garrett Schnack, and our project manager, Dawn Dow. Again, thanks for watching and have a great night.